So the concept of trees in data structures is dealing with a certain type of relationship that is hierarchical in nature. And as we will see, I think it is inspired by the real life tree, like the botanical tree, where you have branches, and each branch goes out to more data items that are somehow related. Now let's take a look at a couple of examples, right? One example is what we call the genealogy tree. So this is the ancestor and descendants relationship. Now, for example, in this case, the beginning of the tree is something that we call the root. Now, in the case of data structure tree, the root is actually at the top, right? It's not at the bottom. But we have one root, and then it's going to branch out from the root. And in this case, let's say it's Abraham, and then Abraham has several children, and they are basically the branches that goes out from the root, right? For example, this is one child, another child, another child, and so on. Now, as we see here, even each of the child in turn have their own children, right? So in that case, then we get a sense that the hierarchical relationship is going to go out, and this tree will continue even as each of the great-grandchildren eventually will also have children, for example. Now, this is just one example of a tree. There are yet other examples. For example, the corporate organization, right? So this could be, for example, at the root, we could have the overall organization itself. And that organization may be decomposed into several different departments. Like R&D is one department, sales another one, purchasing, manufacturing. And in turn, each of these departments may again be split, right, into different types of sub-departments. Now, what we begin to see here is that even as a particular node in the, like a position in the tree, has several children, any one child only has like a single node that is above it, and that is what we call a parent. Okay, we will soon investigate yet other relationship among the nodes. Okay, just another example. This is the file system example. So in this case, you have folders and subfolders. So for example, this could be the main folder that you are dealing with. And within this folder, there could be two subfolders like CS016, CS252, and in turn, each one again would have their own subfolder structures. All right, now how do we then define a tree? Well, in some sense, we can think of a tree in a recursive way. If a particular tree is not empty, right, meaning that it has at least one node, then it has that node called the root with no parent. So root will be the only node in a tree that has no parent, because every other node in the tree will branch out from some parent. Right? Now, each child of the root is in turn the root of another subtree. So for example, if we look at the root here, and the root may have several children, right? And we kind of think each child, for instance, is going to be the head or the root of another subtree. And in this case, the child there becomes the root of another tree, and again they have their own children and so on. Now there is a concept of whether the children or the nodes under a parent are ordered. If it is the case, like in an ordered tree, then there is a meaningful ordering of the children of each node. Okay, let's take a look at an example when that occurs. Now, for example, in this case, you have the content of a book described in terms of a tree structure. So a given book may have the preface, and then it may be organized into several parts. In this case, part A and part B, and then there are references too. Now, it is ordered in the sense that you would expect that the preface is going to come before part A, is going to come before part B, is going to come before references. So it's going to come in a particular ordering, and the ordering is meaningful. Now, in turn, if you go into every node itself, right, and then you look at the children below them, Now even the children are also ordered. So in the sense, like part A here, it has chapter 1, chapter 2, 3, 4, and 5. We probably want to maintain a sense of ordering across these chapters. Because for instance, if we are going to process this tree to undergo certain operations, we may want to maintain that ordering of the chapter. So if we take into account the ordering of the nodes in the tree, and the ordering is actually meaningful, we consider that an ordered tree. Now that we have seen some examples of the different types of, different trees essentially, different instances, we can take a look at some of the relationships between nodes in the tree. Alright, so there are several different things here, like one is the concept of parent, children, and siblings. Okay, so let's say if you go back to this particular example in a sense, now what do we consider to be the parent, for example? Well, the parent and child, that is a particular relationship, right? So for example, in this case, so the book is the parent, part A is the child, right? And that is just one such relationship. Now you have many of those. For example, part A and this, in this case, part A then is the parent, and chapter 5 is then the child. Now this pair of nodes that has a parent and child relationship, we call this an H, right? So there is an H here, there is another H here that connects the two of them. Now in the case we have a consecutive series of edges that are each connected by a node, right? So then we have the concept of a path. So for example, a path is a sequential set of nodes, each connected by parent-child relation, right? Now there are many paths within this particular tree. So for example, if we were to extend it a little bit more, we can go all the way from the top all the way to the bottom, for example, right? Now this is also a path. So basically a series of edges, 1, 2, 3, right? That are each connected by nodes. In that case, this is what we call a path. Alright, so far we've seen the parent, child, edges, and path. Now there are a few other types of relationship that are also meaningful. Okay, so one of them is the concept of siblings. So for instance, we have part B here is a parent of several chapters, right? So in that case, then we call chapter 9 and chapter 6, right? These two are siblings. So they are siblings because they share the same parent, which is part B. Okay. Alright, so one more concept here that is also important is what we consider to be external versus the internal nodes. So, okay, so let me just write it down: external and internal. Now the internal nodes are nodes that has at least one child. So in this particular case, let's say in this tree, right? Okay, maybe this is not exactly the best description of a tree because there is some ambiguity as to whether the tree is completely specified. So let's say, okay, so let's go to a different tree that is a little bit more. All right, so this is a good one. Okay, now in this case we have a tree, and we are going to distinguish between the concept of external and internal nodes. Now the external nodes, all right, no child. The internal nodes, okay, at least one child, right? So it has at least one child. It may have more than one. Now, in fact, here on this particular tree is clearly marked because all the external nodes are the ones that are colored in blue. So this is external, right? And so are all these things, right? Now if you think about this, these are also external in the sense that they are basically they are the outermost part of a tree. Okay, so these are the external ones, and then the ones that are left behind are the internal ones. Now the internal ones are so-called covered by at least one child, right? So then the rest of them are so-called the internal nodes, right? Right? Okay, so now sometimes we also call the external nodes leaf nodes. Okay, so external are also called leaf. Well, individual leaf, plural leaves, right? Okay, so these are some of the important concepts with regards to the tree structure, right? Okay, so maybe just one last thing here. There is an ancestor and descendant, and a node is an ancestor of another node if you can think of it like the grandparent and grandchild relationship, except that it can span any number of intermediate nodes. So for instance, if we were to look at maybe another tree here, so the electronics are out, right? This is the root, right? So the root is essentially the ancestor of everything that is inside the tree. And then if we ask, for instance, for Canada, okay, who are the ancestors of Canada? Canada's ancestor is its parent, international, its grandparent, sales, as well as the great-grandparent. So these are all ancestors, right? And descendants are the ones that are below. So for example, who are the descendants of international? Then it will be all the children, all the grandchildren, and so on until we get to the leaf nodes. All right, so these are some of the definitions that are covered in the case of a tree, right? And let's take a look at what would that abstract data type look like in terms of, for instance, like a Java implementation. Like, what can we do with a tree? Now, in this case, the notion of a tree, right? So it has some of the things that we were talking about before. I mean, we can tell whether or not it's going to be the root, whether or not it's an internal or external node, and that depends on whether or not it has a child, or what is the size. So the size of the tree will be the total number of nodes that are included within the tree. So that means that it includes the root itself, as well as everything that is under the root. And when the size is 0, that is considered empty, right? And there is a notion of parent and children. In this case, like the parent of a particular node, and what are the children of that node. Now, the notion of a particular node here, for now, we're going to mark it as an object called position. The position here is described by an element. This is like a generic implementation. So the element here can be of any type, but it should be a consistent type across within a tree. Okay. All right. So you have the parent of a particular node. You have the children of a particular node, and then you can ask what is the number of children that a node actually has. Now, there could be some partial implementation of that, and that is given by the abstract class here with a number of implementations. For example, if we are looking at whether something is internal, then we just look at the number of children as to whether it's greater than 0 or equals to 0, right? Whether something is a root, well, you can check whether or not the node is a root itself. A number of children, then we just have to iterate over the children, and we just need to count it, right? And the size is going to basically look at every possible positions in the tree. That means this is all the nodes that exist within the tree, and you just increment this. Okay, and all right. So that once we have the concept of a tree, then we can think about what is the depth of any particular node within the tree. And the tree, this depth is attached to a particular node, right? So the depth of the root is going to be 0, because the depth is defined in terms of the number of levels that separate position P from the root. So it means that anything, the root has 0, anything just below the root is going to have a depth of 1, right? So all these have a depth of 1, and the ones that follows below that is going to have the depth of 2, right? So these are going to be the grandchildren of the root, and then the depth of 3, and then the depth of 4. Now, so if we want to figure out what is going to be the depth of any one particular position P, which is a node here, well, that depth is going to be whatever the depth of the parent is, and we increment it by 1, right? Because for example, the depth of electronics RS is 0 because it's a root, and then for its children, their depth is going to be 1 plus whatever the depth of the parent, which is in this case electronics RS, which is 0. So 0 plus 1, and as we go down, we plus 1, plus 1, plus 1, right? And just note that this is defined recursively, right? So you can tell the depth of any particular node just based on how many nodes are above it in terms of the direct ancestor relationship. Now, we can kind of describe what the depth here, and let's put that as dp, right? So which means that the greatest depth is going to be more or less the complexity of the node here, the complexity of the particular operations on the particular tree. Now, if you think about the worst case, for example, what would be the worst case for this? Well, if your tree has n nodes, well, technically the worst case would be the case where you have the greatest depth possible, right? So in this case, maybe you have a tree that essentially branches only in a single direction, and in that case, essentially you have to go from the depth of the last one, for instance, is going to be well, it's going to be a recursive operation that is going to go through every single node in the tree. So in the worst possible case, it's going to be ON. Okay. All right, so that is in the worst case. Now, if you think of it like in the best case, well, what is the best case for a tree of size n? Well, in this case, we don't quite have any limitation in terms of the way that the branching is done. So in that case, what you have would be, well, in that case, you still have to have a root, right? And if the size is n, it means that everything is connected directly to the root. So in that case, you have n minus 1 nodes that is just below the root, but which means that the depth of any node here is no more than 2, right? No more than 1, in fact, because root is 0, so the one that is below it is going to be 1. So in that case, in the best case, this is O1. In the worst case, this is ON, right? This is the worst case. All right, now that's with respect to the depth, and the depth is defined for a node, right? Now you might have also a notion of what we call a height. Now in the case of the height, we are looking at the tree as a whole, like the whole tree, right? And then we are asking, what is its height? What it means is that we actually want to know what is the maximum depth of any one particular node. Now, in this case, the depth of this is 0, and then 1, and then 2, and then 3, and then 4, right? So in that case, the height of this tree is 4, right? Okay, so now how do we tell that height, right, based on the tree? Now, there is one particular implementation that is based on the notion of recursion as well, right? Not in this case, actually not recursion, all right, so okay. This is just a direct implementation. Now, the definition given is that we want to find the maximum depth in the tree. So which means that one possibility is to take a look at, well, the one that has maximum depth would likely be an external node, right? Because if something is internal, meaning that it has a child, so that means that the depth of the child is going to be more than the depth of the parent. So which means you keep going, right? You keep going and then you ask what is the depth of the child instead. So which means that the maximum depth of the tree is going to be the depth of one of its external nodes. One of its external nodes. So one implementation is that you look at every possible position of the node in the tree, and then you check whether or not it's external, because we're only concerned with the external ones. And then we're going to figure out what is the depth of this. And once we figure out what is the depth of it, then we just compare with the current maximum, which is we maintain in the H, right? So in the case of this particular tree, for example, right? And suppose that we are going to, okay, just for assumptions, we are going to access the nodes in different sequences. And let's say this is the first one that we access. So then at this point of time, the H is equals to 1, for example, right? And yet we don't know yet whether that is the maximum. We're going to keep going, right? And the next one that is external is this one, and the height is 2. So now we know that the maximum now is 2. And the next one, let's say, is this, right? So the maximum is now 3. And then we keep going, another external node, no change. But we keep going, we get this external node, and this is now equals to 4. So now we maintain the maximum is now 4. All these external nodes don't change anything because they are of equal height. And then we go to this one, again, this height is 1, so it doesn't replace the maximum. And then this tree, the height, each one of them is 2, the depth, each one of them is 2, so then it doesn't replace the maximum, so we know that the height is 4, right? So that's more or less how this recursion is going to go. Now, unfortunately, this recursion is not very efficient. In fact, in the worst case, it's going to result in the n square worst case time. Okay, so to appreciate why this is n square, okay, so let's analyze it a little bit, and let's make use of a specific example so that we can see it more clearly. Now let's say, for instance, that we have a tree that, okay, let's say looks like this, right? Let's say, right? So we're gonna have the following tree. Now, if we count how many external nodes there are, so we will have 1, 2, 3, 4, 5, right? There are 5 external nodes, right? And we count how many total nodes there are. Well, there are essentially 7 of them, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm sorry, there are 9 of them. Okay, so there are 9 total nodes, right? So let's call that n equals to 9, right? And in this case, the number of external nodes is actually 5, right? And let's say we look at the height of each one of them, or the depth, I'm sorry, the depth, right? Now, the root is 0, so the depth of this one is 1. The depth of this one is going to be 2, right? 1, 2. And then the depth of this one is going to be 3, right? And the depth of this one is going to be 4 and 4, right? 4 and 4, okay? So now let's say this is the case, right? And we realize that, let's say, if we were to continue this, right, indefinitely, now we are going to replace the one on the left here, 4, with, let's say, 2 5s, right? So which means that when we have a tree of size n, right, n here in a specific example is 9. Now, as we see before, the complexity of this depends on more or less on the depth, right? So when the depth is only 1, let's take that as a 1. When the depth is 2, that means that it has to go 2 above, right, to check the depth of the parent and then the depth of the grandparent. And when it's 3, then it's going to check 3 of them. Alright, so now we are going to get a summation more or less in the sequence of 1 plus 2 plus 3 plus 4 all the way until the bottom one, right? And if we look at what kind of summation that is going to be, well, we're going to have 1 plus 2 plus 3 and so on, right? Where do we bottom out? Well, we're going to bottom out at 4, which in that case is going to be more or less about half of the number of nodes, which in this case is going to be n minus 1 over 2, right? And of course, we are still going to have the n minus 1 over 2 that is on the left hand side, right? Which is n minus 1 over 2. All right, okay. Now, so if you take the sum of these things, right? If you take the sum of these things, so 1 to n minus 1 over 2, well, that is going to be n minus 1 over 2 is the total number of numbers here. So that means that I'm going to have n minus 1 over 4 pairs, and each one of them is going to be n minus 1 over 2 plus 1, right? And then I'm going to have another n minus 1 over 2 here. Alright, so n minus 1 over 2 plus 1, well, more or less is going to be n plus 1 over 2, right? Alright, so this is going to be the whole equation. So now we can see here that n minus 1, n plus 1 over 4 over 2. So then this is going to be the same as n squared minus 1 over 8 plus n minus 1 over 2. Now if you simplify that, anyway we only care about the most dominant polynomial, then that's going to give us an on squared worst case time in this particular case. Now that is because we are trying to determine the depth of every node, right? And in some cases we're going to keep repeating some computation. So for example, when we are looking at the depth of this node, right, we're going to look at the depth of the parent of this one, of this one, of this one, right? And yet, when we are looking at the depth of 3, we are also looking at the same nodes, right? Which means that there are many times when we are repeating essentially the same computation again and again. So a better way of doing that is to try to save on all these different computations. Now, so which means that a slightly different implementation to this is going to have the following. So we are going to return the height of the subtree that is rooted at the position P, right? Now in this case, let's take the root itself as the position. So now what we're going to say is that, okay, let's branch out to the children, and this is going to be given by the for loop here. We're going to branch out to the children, right? And each time we are going to see that the maximum height, right? The height of a particular node, the height of a particular node is going to be the maximum between the current height and 1 plus the height of the child. So in this case, it means that we look at the smallest possible tree, and then let's say there is a tree of size 1. Let's say we are now at the leaf, right? And we say, okay, what is this height? Well, the height of this, because it doesn't have children, is going to be 0, right? And then, alright, so now which means that all these leaf nodes, they're all going to have zeros, right? Then when we get to the parent, and the parent is going to say, what is my height? My height is the height of all my children, right? Or any of my children. I'm going to take the maximum between that as well as the 1 plus the 1 plus the height of any children, right? In that case, there was 0 before, so now it's 1, right? Now, this is 1. Now, the height of South America is 0. The height of Canada is 1. So, by the time we come to international, then we are going to say, all right, so the height that I'm going to have is going to be, basically, I'm going to add 1 to each of my child. And then I'm just going to find my the maximum of all that. So, Canada plus 1, America plus 1, overseas plus 1. So the maximum is now 2, right? And then we're going to keep going. And as we go up, we are essentially incrementing that. Now the complexity of doing this, because we only need to visit every single node exactly once. So, and if there are n nodes in this tree, then you're going to have a complexity of just O(n), right? So in this case, it turns out that even to do the same thing, which is height, we can arrive at different implementations that might either be O(n) squared or O(n).